Hello everyone, I'm Jo Ashbourne, the Director of the St Cross Centre for the History and Philosophy of Physics, and I'd like to warmly welcome you all to today's special event in association with Oxford's Department of Physics. We have nearly 1,500 people joining us today from all around the world, so good morning, good afternoon, and good evening from across the time zones. We're delighted to welcome Professor Michio Kaku to speak on Physics of the Impossible Revisited. Michio is a professor of theoretical physics at the City College of New York and is the author of the New York Times bestselling books Physics of the Impossible, Physics of the Future, and The Future of the Mind. As an acclaimed popularizer of science, he's also hosted several TV programs for the BBC, the Discovery Channel, the History Channel, and the Science Channel, as well as hosting a very popular weekly radio program. But perhaps topping all that, Michio's highest accolade yet just might be that a British rock band's album is based on one of his books. There will be time for questions after the lecture, and these can be typed into the Zoom Q&A box at the bottom of your screen. Michio, we're very much looking forward to your lecture. Thank you.
I'm a professor of theoretical physics, and professionally I work in something called string theory. In fact, professionally I work in the 11th dimension. But today we're not going to talk about the 11th dimension so much. We're going to talk about the impossible. Now, my first introduction to the impossible was when I was 8 years old. When I was 8 years old, something happened which changed my life. You see, at that time, all the newspapers published a picture of a man's desk. And they said that this scientist, one of the greatest scientists of our time, could not finish this manuscript. It was unfinished. In fact, some physicists even said it's impossible to finish this manuscript. Well, I was fascinated. What could be so hard that the great scientists of our time could not finish this theory? So I went to the library, and over the years, I found out that this man was called Albert Einstein. And what he failed to complete was the impossible, a theory of everything that would unite all the forces of the universe into a single equation. And in fact, Wolfgang Pauli, another Nobel Prize winner, once said, quote, "What God has torn asunder, let no man put together." In other words, we have the gravitational force, the electromagnetic force, the weak and strong nuclear forces. What God has torn apart, let no man put together. Well, today we're going to talk about the impossible. That is, yes, we physicists are working on things that may seem impossible, but actually may be well within the realm of possibility. So I'm going to ask a question, a simple question. What is truly impossible 1,000,000 years from now? You know, when I watch a science fiction movie, sometimes I count how many laws of physics are being violated on that Hollywood movie screen. But then I realize, wait a minute, I'm assuming that the laws of physics don't change over the centuries. What about the laws of physics 1,000,000 years from now? Well, in my books, I try to convey what we know and don't know about the science of today. I've interviewed over 300 of the world's top scientists for BBC television, the Discovery Channel, the Science Channel. And I've put down a lot of their thoughts in my books. Physics of the Future, talking about artificial intelligence, robots, biotechnology, the future of the mind when the human mind is connected to the internet, and telepathy, telekinesis become our way of communicating. In Physics of the Impossible, of course, I talk about the impossibility of the technologies of today. And in The Future of Humanity, I talk about the fact that our destiny could be in outer space. You know, the dinosaurs did not have a space program, and that's why they're not here today, but we do. So again, when I was 8 years old, I was mesmerized by this picture. I was mesmerized by the fact that a great scientist attempted the impossible, to unify all the laws of physics into a single equation. However, I was only 8 years old. On Saturday mornings, I used to watch the Saturday morning shows. In particular, I used to watch Flash Gordon. And I watched Flash Gordon with his ray guns, starships, invisibility machines, cities in the sky. And I said to myself, wow. But I realized later on that this was, of course, fiction. What about the science? And then I began to realize something that Arthur C. Clarke once said years ago. You see, I had two passions in my life. First is physics, theoretical physics, and the unified field theory and string theory. But I was also fascinated by the future. Years later, I learned that the key to understanding the future is a firm foundation in physics. As Arthur C. Clarke once said, any sufficiently advanced technology is indistinguishable from magic. And that's what we're going to talk about here today, magic. And T.H. White once wrote that, quote, everything not forbidden is compulsory. Think of, for example, time travel. Is time travel really forbidden? Well, the late Stephen Hawking even proposed something called the chronology protection hypothesis, a principle that showed that time travel was impossible. But he couldn't prove it. In fact, it's still unproven even today. So what is not forbidden is compulsory. If we cannot disprove the principles of time travel, then we must have time travel. Well, I'm not the only dreamer of the impossible. There's a long string of people who also dreamed of the impossible. Robert Goddard here is the father of modern rocketry. When he was a child, he climbed up a tree, looked up in the heavens, and saw Mars. And he made a promise to himself that one day he would build the machines that would take us to the moon and maybe even Mars. His dream was so impossible that the New York Times published an article denouncing his work, calling him a fraud. Because, of course, said the New York Times, everybody knows that rockets cannot move in the vacuum of outer space. Well, decades later, long after Robert Goddard had died, and humans walked on the surface of the moon in 1969, the New York Times issued an apology. Oops, I guess it is possible that rockets can do the impossible, move in the vacuum of space. And then there was Edwin Hubble, the greatest astronomer of the 20th century, a graduate of Oxford University. He was a Rhodes Scholar, destined to become a lawyer. That was his career path that his father and his family wanted him to pursue. But he remembered reading about the impossible as a child. Jules Verne. He remembered the works of Jules Verne. So he quit his law practice, went to the University of Chicago, got a PhD, and went on to discover the expanding universe, which makes possible the Big Bang Theory. And then there's Carl Sagan, the noted astronomer. When he was a child, he read John Carter of Mars and dreamed about one day roaming across the sands of Mars. And then Freeman Dyson, the late Freeman Dyson shown here, he dreamed of starships that would one day take us to the stars. So we'll talk about the practicality of building one of Dyson's starships. But let's talk about the impossible. I say that there are at least three kinds of impossibilities that we have to rank. First are the plausible impossibles, things that may be possible within a few decades, maybe a few centuries, things that are well within the known laws of physics. Invisibility, nanotechnology, replicators, telepathy, telekinesis, even immortality, quantum teleportation, space elevators, sublight starships. Believe it or not, they are all possible. You see, I'm not an engineer. I'm not going to talk about how much money it's going to take to build these things. I'm just going to say that it is well within the known laws of physics to create invisibility shields, telepathic helmets. Then there's the probably impossible, that is physics at the Planck energy. You see, Einstein's equations eventually break down. They break down at the center of a black hole, and they break down at the instant of the Big Bang. Einstein's equations are useless at the two most intriguing points in space and time, the center of a black hole and the instant of creation. But that's where the Planck energy comes in. New laws of physics emerge as we quantize gravity and we go to things like string theory, a multiverse, pre-Big Bang universes, things that are probably impossible, but stretch the boundaries of known laws of physics, which collapse at the instant of the creation of the universe. And then we have things that are just downright impossible. For example, maybe the conservation of matter and energy. But I began to realize when I watch a Harry Potter movie, I list all the laws of physics that are violated, pulling a rabbit out of a hat. But then I say to myself, that's an engineering problem. Is it a physics problem? That is, molecule for molecule. Is there a law of physics that prevents me from changing a rabbit and pulling it out of a hat? And then I begin to realize that there are actually very few laws of physics violated in a Harry Potter movie. But let's talk about a few of them. One of the most ancient impossibilities written about by the Greeks is invisibility. Plato, 2,000 years ago, once used invisibility to prove that you needed a philosopher king to rule the world. Humans, individuals could not be trusted to run empires. And he argued as follows, that if somebody, an average person, were to discover the secret of invisibility, he could quickly invade the palace, he could seduce the queen, he could kill the king, and become the next emperor. In other words, humans cannot be trusted with the power of invisibility because it is so great, the temptations are so great that it would corrupt any honest individual. But today, believe it or not, we are working on invisibility. And guess who's paying for it? The military. The military invested billions of dollars to perfect stealth bombers and now is working on bombers that are totally invisible, perhaps. This is the area of what are called metamaterials. That is, light can actually wrap around an object, reform at the other end, such that the object inside, shown here, is invisible. Now, when I teach optics to my physics students, I tell them that the bending of light is given by an index of refraction which is greater than 1. But what happens if the index of refraction becomes negative? It turns out that that is within the laws of electricity and magnetism to have a negative index of refraction. So that light does bend and wrap around an apple, shown here, reforms at the other end. Think of an apple in a river. Water wraps around the apple, reforms at the other end, and the object inside is invisible. Now there's a catch here. The catch here is that for microwaves, we've already done it. On the left, you see an obstacle in the way of a wavefront of microwave radiation. On the right, you see that obstacle made out of metamaterials, materials with a negative index of refraction on microwave radiation. And sure enough, the electromagnetic wave wraps around the object, reforms at the other side, so it is invisible. Now, under light, of course, it is visible. This is what it looks like. You have the object in the center, and then you have coils representing circuits that take microwave radiation, shoot them back in the wrong direction, giving you a negative index of refraction. So of course, what we want is invisibility in the optical range. We do not have that yet. We're getting close. However, objects have color. Objects are invisible when you move your head. So invisibility turned out to be a lot harder than we thought. So we do not yet have true invisibility. Now we have stealth bombers. Stealth bombers simply diffuse radar, diffuse it so that a stealth bomber has a radar signature of a large bird. It is not true invisibility. True invisibility requires nanotechnology. Nanotechnology on a level that we do not yet have. However, we're getting close. We're in the process of now of building atomic machines. Nobel Prizes have been given to people pioneering the idea of atomic machines. Machines that are stronger than steel, machines that can self-replicate, machines that can compute, and machines that can be programmed. This gives us the possibility of programmable matter. We can program software and hardware, but we cannot program a lump of coal. But with nanotechnology, the dream is a second industrial revolution. Now, the key to this second industrial revolution is what is called a nanobot. A nanobot, we don't have them, but in principle, it's possible to build a machine that is smaller than a blood cell. And in fact, we have nanoparticles already being experimented with in the United States and elsewhere. In Bethesda, Maryland, the National Institutes of Health are using nanoparticles to kill cancer cells one by one in the blood. So this is no longer totally in the realm of science fiction, attacking cancer cells at the scale of cells, one by one, with what are called nanoparticles. But of course, the dream is to have a molecular assembler. You know, in Star Trek, they have the replicator. The replicator takes apart an object atom for atom and then reforms it into anything you want. And the question is, does that violate the laws of physics? Well, believe it or not, there's a rather healthy debate going on about that precise question. Does a nanobot disobey the quantum theory? It turns out that at the level of the quantum theory, new forces emerge which are quite unexpected. We can build, for example, tongs and levers and gears and pulleys that are atomic in size. But can they be manipulated like a lever, a pulley, a hammer, or a straw? And this is where quantum effects get in the way. We have something called the Casimir effect. The Casimir effect takes place when quantum objects get very close together. The Casimir effect gives you repulsive and attractive forces at the atomic scale. These forces are unusual. They have positive and negative energy. Now, we never thought that negative energy could even exist. That was once considered an impossibility. You talk to Newton, you talk to Einstein, and they would say, bah, humbug. There's no such thing as negative energy. But that's what the Casimir effect does. It gives us negative energy. It's a very strange world, the world of the nanobot. And we'll get back to this when we discuss time travel. Because if you could harness vast amounts of negative energy, you could, in principle, build a time machine. But we'll get into that in a moment. So this is the dream. This is the dream of people who work on nanotechnology and nanobots, a replicator, a molecular assembler, to create something out of nothing, like out of Harry Potter. So when I watch a Harry Potter movie, I say to myself, if he can change one thing into another, can we do it as well? Does this disobey the known laws of physics? That's the question that we have to ask ourselves. Well, it turns out that Mother Nature is the greatest nanotechnologist of all. A nanobot does exist. In fact, Mother Nature can take a pile of hamburgers and French fries, manipulate the hamburgers and French fries atom for atom to create a baby in 9 months. That is a miracle of nanotechnology, to convert hamburgers and French fries into a human baby in 9 months. So how does Mother Nature do it? We have to realize that the wheel has already been invented. Why reinvent the wheel when Mother Nature has already done it? Mother Nature uses something called the ribosomes. Ribosomes can take on the upper left amino acids, hamburgers, French fries, and combine them atom for atom to reassemble RNA, the genetic material, and then eventually DNA. So in other words, nanobots do exist. The question is, can we harness the power of Mother Nature to create a nanobot to give us a molecular assembler? And at the present time, the answer is no, but at least we're onto something. Why reinvent the wheel? Mother Nature has already done it. And then moving on to the question of the impossible, the United States Pentagon and the CIA spent millions of dollars, tens of millions of dollars in the 60s and 70s trying to perfect MK Ultra, the top secret plan to perfect psychic powers, telepathy, telekinesis, remote viewing, you named it. The Pentagon and the CIA funded 80 top American universities, the cream of the American intellectual elite, to work on bizarre technologies straight out of a comic book. Why? Because the rumor spread within intelligence circles in the United States that the Russians were working with psychics. The Russians were working with fortune tellers, with hypnotists, with telepaths. And if they can do that, if they can brainwash our troops in Korea, they have mind control. And so the military spent tens of millions of dollars on something called MK Ultra. Google it on the internet, and you can see some of the bizarre schemes they funded. For example, they would ask psychics to go up to a map of the world with pins, and they were asked to stick pins in the ocean to locate Soviet nuclear submarines. Well, of course, these psychics couldn't get a single one correct, but that didn't stop the Pentagon from funding this research because the Russians were doing it. Well, today we do have telepathy. We do have telekinesis. We do have many of the things that were once considered impossible back in the 1950s and 1960s. This is BCI, brain-computer interface. We connect the living brain to a microchip at Brown University, at Johns Hopkins University, connect it to a laptop, and connect the laptop to the internet or to a machine. For example, this individual here is paralyzed, but she can create music just by thinking about it. And these two individuals here, they're also paralyzed, but they communicate mentally using the power of the internet. So in other words, you can connect the brain to an avatar. On the left, you see Asimo, a robot controlled telepathically by a human. Now you are seeing perhaps the future of space travel. If space travel turns out to be very dangerous, then why not control an avatar with the human mind? And for that matter, as I will talk about in a minute, why not digitize the human mind and let the digitized software of the human consciousness enter an avatar and let the avatar control a robot on another world? And on the upper right, you see what they do in Japan. In Japan, you can buy a headband that you put around your head at a party. The headband is connected to 2 ears. When you talk to someone very interesting at a party, the 2 ears light up. But if you talk to someone at a party who's very boring, the 2 ears droop. So in Japan, you always know if you're going to go home alone after a party. So telepathy, telekinesis are here today. Still very primitive, but we've now made inroads into connecting the mind to the internet. And then we had the Connectome Project, even more ambitious. The Genome Project revolutionized all of medicine. Doctors, biologists, they start with the genome. In the future, scientists will start with the connectome, because the connectome project is to map every single neuron of the living brain. You realize already the world's record is we have now, by slicing and dicing, mapped every neuron in the brain of a fruit fly. There are 100,000 neurons in the brain of a fruit fly, all of which have been decoded using computers. Now we have 100 billion neurons, so it's a very arduous task to sequence the neurons of the brain, human brain, but it is definitely possible. Possible, but realize that the human brain is the most complex object in the known universe. Think of the known universe. What is the most complex object in that universe? It is the human brain. And it's being funded by the military, also funded by doctors, because mental illness can be cured perhaps by looking at MRI scans of the living brain. For example, the left part of the brain governs voices. Verbal commands are constructed in the left part of your brain. The front part of your brain is your conscious brain. But in a schizophrenic, you can see that the left part of the brain lights up. The brain is talking to itself without the knowledge or permission of the front part of the brain. In other words, that is madness. Madness is when you are unaware that there's a part of your brain firing, creating voices without your permission. So we can now see mental illness in action. We can actually see it by probing the blood flow of the brain using MRI machines. Not only that, but we can now record memories. This gives us visions of another impossible movie, and we're talking about The Matrix. In mice, for example, the memories are concentrated in the hippocampus, shown here in the human brain, and scientists have put electrodes on either side of the hippocampus and recorded memories being made by mice brains. And then by putting the memories back into the brain, the mouse would remember it. So in other words, memories can now be recorded. Next, scientists are working with primates. We're now recording the memories made by primates when they perform simple tasks. After that, maybe Alzheimer's patients. That is the disease of the century. We could have tens of millions of people wandering the streets, wondering, where do I live? Who am I? Where am I? Perhaps in the future, we'll have a memory chip shown here. And who is funding that? The United States Pentagon, because there are so many GIs from Afghanistan and Iraq with spinal cord injuries, with memory problems. Why not give them the benefit of memory once again? And for that matter, another impossibility is photographing a dream. Maybe you've seen the movie with Leonardo DiCaprio, where he enters into people's dreams. Now you may say to yourself, that's obviously impossible, but no, it's possible. On the left, you see the living brain and blood flow in 30,000 points cataloged by computers. So with MRI machines, we can locate 30,000 points of blood flow, measure the extent of the blood flow, and create a computer map, an MRI map of the blood flow of the living brain. Put that into a software of a computer, the computer chugs and chugs and chugs and spits out a picture of what you were thinking of. Here on the top, you see the actor Steve Martin. Below that is an image created by 30,000 pixels in a computer monitoring the MRI scan of the blood flow of 30,000 dots in the living brain. This means that eventually we'll have much finer resolution pictures. And one day when you go to sleep, perhaps we'll photograph that dream. Yes, it is now in principle possible to photograph a dream. You see, when people are put into an MRI machine, sometimes they fall asleep, but the machine keeps on going, printing out a very rough picture of what you are dreaming of. And this could also prove or disprove another impossibility, lucid dreaming. Lucid dreaming is when you are conscious while dreaming and you control the direction of your dream. Many people thought that was fantasy controlling your dream, but it's true. In fact, at the Max Planck Institute in Leipzig, Germany, they put a lucid dreamer in an MRI machine, and sure enough, it's true. He was conscious. The prefrontal lobe was fully lit up, while the centers governing the dream, the hippocampus, were also lit up simultaneously. So think about that. One day in the future, you'll wake up, you'll push a button and see the dream that you had the previous night. Just don't tell your wife or husband about it. And who's going to use this technology? Artists. Artists will love the idea that they can imagine something and have it printed on a laser printer right before their eyes. Every time there was a revolution in the way we manipulate images, it created an explosion of art. Ever since we carved stone objects in stone and rock to creating objects made out of paint, and now we can manipulate pixels on a computer screen. In the future, we will manipulate images in the mind itself. And this will give us BrainNet. People sometimes ask, what is the next revolution in the internet? I think that years from now, the next level of the internet will be BrainNet. We can already record simple memories. That has already been done. We've sent them on the internet. In the future, we will record emotions, feelings, sensations, and put that on the internet. That will revolutionize entertainment, revolutionize human interactions. After all, what is the movies? What is television? A two-dimensional screen with sound. That's it. Hasn't changed much in 50 years. A two-dimensional screen with sound. That has revolutionized entertainment. But you know, a long time ago, we used to have silent movies. Charlie Chaplin was very famous during that era. But when sound came in, who wanted to see Charlie Chaplin anymore? They wanted to hear sound. Next, people want to feel emotions, memories inside their entertainment. And we will look back at the movies as an ancient form of entertainment. Teenagers will love it. Teenagers already put a happy face at the end of every sentence. In the future, they'll put the emotion, the memory of their first kiss, their first dance, their first date on the internet. And this will also change the way humans deal with other humans. When some people talk about their suffering, other people say, yeah, sure. They don't believe it, that other people can suffer. But if you can feel their suffering, then perhaps it'll promote human communication. And another possibility is to digitize the mind itself. In other words, at Silicon Valley, there's already a company offering to digitize your electronic signature. Everything known about you, your credit card transactions, Instagram, emails, everything digitized to create a digital copy of you. You know, if you research your family tree, you go back maybe 2 generations and then it stops. It stops. Your ancestors, they just left 2 lines in a book in a church, their birth date and their death date, and that's it. A human life summarized in just 2 sentences, because that's all there was back then. In the future, we will digitize your personality, everything known about you. And this will revolutionize the library. The library today has many books about Winston Churchill or Einstein. In the future, you will talk. You will talk to Winston Churchill. You will talk to Albert Einstein. I would love to talk to Einstein. I would love to talk to a digitized image that has access to all his thoughts, all his letters, all his dreams, his books. I would love to be able to talk to that person. And when we are digitized, you will talk to your great, 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 great grandkids, and they will talk to their great, 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 great grandparents that they've always read about in their history books. This is called digitized immortality. But not only that, but I think that one day when we have digitized immortality, what do we do with it? We put it on a laser beam and shoot it to the moon, shoot it to Mars, and explore the universe at the speed of light. This is well within our technological capabilities. First of all, if you digitize the human mind, digital information easily can be put on a laser beam, and the laser beam in 1 second can rocket to the moon without booster rockets, without rocket failures, without weightlessness, without cosmic rays, without accidents. That's the way to go, at the speed of light. In 15 minutes, you're on Mars. 4 years, you're on the nearest star. And what do? We put a mainframe on the moon, we shoot our consciousness to the moon and download it into an avatar. The avatar is superhuman. It could walk on Mars, thrive on the moon. It is a robot with your personality, your memories, that has rocketed through the universe at the speed of light. Think about it. Consciousness exploring the universe at the fastest velocity known so far, the speed of light. In fact, I'll stick my neck out and say that maybe, just maybe, this already exists. Aliens in the world, in the galaxy, maybe years ahead of us, may have already realized that rockets are not the way to go. Perhaps laser porting is the way to go, to send your consciousness throughout the universe at the speed of light, the fastest velocity in the universe. And that's the way to explore the universe, in the body of an avatar, which is superhuman, which is super handsome, super pretty, can breathe on any atmosphere or no atmosphere at all, and explore the universe at the speed of light. Well, you may say to yourself, that's all nice, but that requires a lot of computer power. It takes a lot of computer power to digitize the human mind. Well, let's talk about the limits of computation now. We are now entering the end of the age of silicon. Silicon power has taken us in the last 50 years from the machine age to the vacuum tube age, all the way to the internet age of today. This is Moore's law. The computer power doubles every 18 months because we can etch smaller and smaller components on a silicon chip. That is the trillion-dollar idea, using ultraviolet radiation to etch smaller and smaller transistors on a silicon wafer. But all things must pass. Moore's law is slowing down. You see it in every graph. Yes, Moore's law is slowing down. Why? First, we have Heisenberg uncertainty. We don't know where the electron is anymore. It leaks. Leakage takes place. And heat, huge amounts of heat is being generated. So we have to go to the post-silicon era. So in other words, one day, Silicon Valley could become a rust belt. There could be unemployment there with all these silicon software engineers out of work. So we have to go to the next step, but we're not ready yet. Sorry about that. The next step is quantum computers. Computers that compute on individual atoms. Now, quantum computers are extremely delicate, very hard to build. Shown here, for example, is a picture. Most of the coils you see here are cooling coils, because you have to get down toward near absolute zero when atoms vibrate in unison. And in fact, progress has been made. Google reported recently that its quantum computer can actually beat many supercomputers made out of silicon. That made headlines, but let's put things into perspective. That was a one-trick pony. That's all this machine can do. This machine is not an all-purpose AI machine. You cannot joke with it. You cannot slap it on the back and say, congratulations, you just beat a silicon computer. No, we have a long ways to go before quantum computers enter the commercial marketplace. You see, the problem is decoherence. Ordinary light, we know, is a jumble of different frequencies and phases. It's incoherent light, decoherent light. Laser light is coherent light. All the light beams vibrating in unison. That's laser light. So the slightest vibration can destroy the coherence of atoms vibrating inside a quantum computer. That is the problem. Now we're making progress now, as I mentioned. Every year, a new record is being broken by quantum computers. But a quantum computer that you can put on your wristwatch that is as convenient as a silicon computer, we're still decades away from that. But there's money being poured into this. Money from the Pentagon, money from private industry. By the way, we know from documents released by leakers that the CIA definitely is interested in quantum computers, but it decided that it's still too early to begin the commercialization of that technology. But with quantum computers comes the possibility of teleportation, another impossible technology that we see on Star Trek, where you beam up by having the atoms of your body dissolve and then radioed to a distant place where it's reassembled. Well, believe it or not, quantum teleportation is a reality shown here. We can now teleport information to outer space. Eventually, in 2024 or so, we will go back to the moon, and already people are talking about teleporting information to the moon. Here's how we do it in a nutshell. Look at the green arrow, A, the green arrow. That's the original signal. Now look at the upper right. In the upper right, you see another green arrow, that's C. We want the information from A to go to C. To do that, you need an intermediary. The intermediary is BC, shown here, two particles that are intertwined that vibrate in unison. In fact, believe it or not, information can travel between B and C faster than the speed of light. Now, of course, Einstein hated that idea. That's why he even proposed this idea of entanglement to show that the quantum theory was preposterous, that the quantum theory said that information can travel faster than light. Well, in some sense, it does. In that sense, Einstein was wrong. But let's be fair about this. Einstein has the last laugh because the so-called information that goes between B and C is actually random, useless information. You cannot send Morse code. You cannot send usable information from B to C faster than the speed of light. Sorry about that. But quantum teleportation does allow you to send information from point A to point B at sublight velocities. Quantum teleportation exists. How long will it take before we can use that commercially? Maybe centuries. Now, years ago, there was a Russian space scientist by the name of Tsiolkovsky, one of the founders of the space program. And he witnessed the Eiffel Tower being built. And then he had a dream. He dreamed of what happens if they just kept on going. What happens if the workers in Paris didn't stop building the Eiffel Tower, but just kept on going? And he asked himself a simple question: how far can you go? Well, he realized that if you could build a wire, a cable, into outer space, it would not fall down. Centrifugal force, the spin of the Earth, would keep the object whizzing around the planet Earth. And using a simple calculation, you could calculate that, yes, a space elevator is theoretically possible. So what's the catch? There's always a catch here. Why did Tsiolkovsky give up the idea of a space elevator? Because the tension on that cable would snap steel. Nothing known to science back then could withstand the stress of a centrifugal force of being whipped around the Earth. Well, today we have nanotechnology. nanotechnology is in principle tough enough to create a space elevator. What's the problem? Well, of course, economics, building one of these things, but the cable has to be pure. It has to be pure graphene, carbon nanotubes without perfections. A nanotube with imperfections can vastly reduce the strength of the cable, and the cable might snap. There are other problems with a space elevator. Because Earth has satellites, satellites do change with each revolution. Eventually, they'll strike the cable. So the cable has to be maneuverable. It has to wiggle its way out of way when the space station or satellites come whizzing by. But it is well within the laws of physics. It is a huge engineering problem to create pure carbon nanotubes that can take us into the heavens. And speaking about the heavens, why do we even want to go into outer space? Well, as I said, the dinosaurs did not have a space program. That's why they're not here today to discuss this question. And 99.9% of all life forms eventually go extinct. Extinction is the norm. If you don't believe me, just dig under your feet and you can see the fossils of 99.9% of all life forms that are extinct. So let's dream about starships. Freeman Dyson and Ted Taylor worked on a design to use mini nuclear weapons shot out of the exhaust of a starship to reach a good fraction of the speed of light. And by golly, it would work. In principle, Project Orion and Daedalus can actually use nuclear weapons to boost themselves to a good fraction of the speed of light. This is a practical design. It will actually work. It is well within the boundaries of engineering and physics of today. So what happened? Well, I talked to Ted Taylor once. Ted Taylor designed many of the United States atomic weapons. He designed, for example, one of the smallest nuclear bombs ever detonated, the Davy Crockett. He designed most of the United States arsenal. And I asked him, why did you abandon a starship? And he said very frankly that one day his technology would be used to create mini nuclear weapons that can fit inside of a suitcase that could devastate an entire city. And the horror that his technology could be used to devastate entire cities was too much. He said, no, I cannot work on Orion because it'll open the door to terrorists. But that didn't stop other people from dreaming of starships. Here's a starship that uses interstellar space as the fuel. It's an ice cream cone shown here. The ice cream cone moves in the forward direction, scooping up interstellar gas, fusing it, and then giving us exhaust forever. It'll run forever because interstellar gas is everywhere. Well, yeah, in principle, that might work if you have enough hydrogen gas out there. Another design is antimatter rockets. Yes, antimatter rockets will work, but it's a huge engineering problem because the cost of antimatter would bankrupt any modern country. So civilizations of the future may harness even greater power. Type 1, according to Nikolai Kardashev, harnesses the power of an entire planet, like Flash Gordon or Buck Rogers. Type 2 harnesses the power of a star. Type 3 harnesses the power of an entire galaxy. In order to access these energies, you may want to become a type 3 civilization. A type 3 civilization now enters the world of the Planck energy. The Planck energy is the energy at which Einstein's equations break down. The quantum theory takes over, and to understand the center of a black hole, you have to understand the Planck energy. Well, Einstein in 1935 took two black holes, stuck them back to back, and created the first wormhole. Well, Alice in Wonderland, even before then, Charles Dodgson, otherwise known as Lewis Carroll, an Oxford professor of mathematics, realized that if you take two universes and stick them together with a looking glass, you can create your wormhole. And in 1963, Roy Kerr, mathematician, showed that a spinning black hole does not collapse to a dot at all. It collapses to a ring that you can perhaps negotiate your way through. And then yet another design was devised by Michio Kaku, the Alcubierre drive. I talked to him once and I said, Miguel, what gave you the idea for yet another way to go faster than the speed of light? Not to punch a hole in space, but to compress space. So instead of going to the stars come to you. And he told me that he was watching an episode of Star Trek and said, hey, I can devise a solution of Einstein's equations, which can also compress space in the forward direction of the Enterprise and give us faster than light travel. Well, what's the catch? There's always a catch someplace, otherwise you would have these machines already. First, you need positive energy on the scale of a black hole. And then you need the Casimir effect that we mentioned earlier, negative energy. And negative energy stabilizes the black hole. Now, what could you do with it? Perhaps create a time machine. You see, a wormhole may connect you not just to another universe, but to the same universe in a distant time. And so wormhole may also be used as a time machine as well. But of course, time machines have problems, and that is you have contradictions. For example, Robert Heinlein once wrote a short story whereby you became your own mother, your own father, your own son, your own daughter. One man becoming their own mother. Impossible, right? Well, it's possible if time travel is possible. But the question is, can you say anything meaningful about time travel? And the answer is no, because Einstein's equations break down at the instant of creation at the center of a black hole. And the Large Hadron Collider has given us the standard model, but the standard model also is not powerful enough to probe the Planck energy. In fact, the standard model shown here is a theory of almost everything except gravity. The theory of almost everything makes no mention of gravity, has 23 parameters, 3 generations of identical particles, splices the weak, strong electromagnetic forces by hand. It is a theory only a mother can love. There are two conflicting views with this. The Greeks, once again, pioneered these two opposing points of view. Democritus believed in atoms. Atoms are the basis of reality. But Pythagoras said, no, music, resonances, the music of a violin string, a lyre string, a piece of metal that has been hit by a blacksmith. Strings, he said, are the basis of reality because strings give us resonances that give us the universe. Well, today, the leading and only theory which combines gravity with the standard model is string theory. String theory says that if I look into a microscope, a super microscope, I can see that subatomic particles are nothing but notes on a tiny vibrating string. Physics is the harmonies of the string. Chemistry is the melodies we can play on interacting strings. The universe is a symphony of strings. And then what is the mind of God? The mind of God is cosmic music resonating through hyperspace. Now, of course, every theory has to be tested, but there are ways to test string theory by looking for dark matter, deviations from Newton's inverse square law, new particles from replacements for the Large Hadron Collider that are now being discussed in China, Europe, and in Japan, and detecting gravity waves. In the future, we will put the next gravity wave detectors, the next generation, in outer space. This is LISA, a device that is 3 million miles across, perhaps capable of detecting radiation from the instant of the Big Bang, and maybe even before the Big Bang itself. String theory, of course, is bizarre. I have a whole lecture about string theory. It talks about a multiverse of universes. It talks about hyperspace. This is Salvador Dali's Crucifixion, where Jesus Christ is crucified in the fourth dimension. And string theory and inflation predicts a multiverse of universes. Think about that, a multiverse of universes that may even give us how the universe will die. You know, in closing, let me say that Bertrand Russell, the British mathematician, once wrote the most depressing passages in the English language. I'll paraphrase. He said that one day the sun will die, and all life on earth will die with the sun. All the tears, all the triumphs, all the achievements of humanity are for nothing, absolutely nothing when the sun dies. Well, today we know that we have rocket ships that can take us into outer space, but what happens when the universe dies? When the universe dies, trillions of years from now, perhaps our only hope is to harness the impossible, and that is to create a wormhole, a baby universe in the multiverse of universes, an escape hatch, so that we can escape to another universe and perhaps mess up that universe as well. Well, let me now end on one last story. And when I was a child, my role model, my hero was Albert Einstein. And let me tell you my favorite Einstein story. When Einstein was an old man, he was tired of giving the same talk over and over again. So one day his chauffeur came up to him and the chauffeur said, "Professor, I'm really a part-time actor. I've heard your speech so many times, I've memorized it. So why don't we trade places? I will put on a mustache, I will put on a wig, I will be the great Einstein, and you can take a rest and be my chauffeur." Well, Einstein loved the joke, so they switched places. This went along famously until one day, a mathematician in the back asked a very difficult question. And Einstein thought, the game is up, the game is up. But then the chauffeur said, "That question is so elementary that even my chauffeur here can answer it for you." Well, thank you very much. That ends the lecture. And what I'd like to do now is take some calls from the audience. This is your chance to ask a question, make a comment. Well, the questions are coming right in. So let me read some questions and try to answer them. One question is, do you believe that aliens are humans coming from the future? Well, I'm a scientist. I believe that statements like this have to undergo three criteria: testability, reproducibility, and falsifiability. The question of aliens from outer space is at the present time not testable, reproducible, or falsifiable. However, that doesn't mean that we haven't been visited. Maybe we have, but at the present time we have no reproducible evidence. However, the most intriguing evidence are, of course, these UFO sightings by the United States Navy. We now have not one, but an ocean of videotapes showing our encounters with objects traveling between Mach 5 and Mach 20. Now, of course, hypersonic devices being perfected by China, the United States, and Russia can also go between Mach 5 and Mach 20. But these devices can whip around with centrifugal forces, would crush living flesh, and they have no exhaust, and they have no sonic boom. That is a mystery. How can you go from Mach 5 to Mach 20 without creating a sonic boom? That is a question that we don't know the answer to. Here's another question. Is the universe deterministic or not? Well, if you believe in the quantum theory, the universe is quantum mechanical. But then the question is, why does the universe look so deterministic, so Newtonian? Well, personally, I believe in the multiverse idea, which comes out of string theory, inflation, the quantum theory, and the many worlds interpretation. If you learn quantum mechanics, and I teach quantum mechanics sometimes, you learn that there are several postulates to the Schrodinger equation, but the last postulate is the wave function collapses and mysteriously becomes the world we're familiar with. Well, the many worlds idea is even simpler than that. You simply drop the last assumption of quantum mechanics, and the wave function merrily goes splitting left and right. Each universe looks deterministic. Each universe looks Newtonian, in fact, but the multiverse shows that there are infinite number of copies of ourselves in a universe that is constantly bifurcating. And then here's another question. In a multiverse, then what is the universe? How do we define something that is outside our universe? Well, the first question that children ask is, when they hear about this, is if the universe is expanding, what is it expanding into? Well, there are two ways to answer that question. One is it's basically a sheet of paper that is simply being stretched. It's infinite, simply stretching a sheet of paper in all directions. That's the traditional mathematical way of looking at the expanding universe, but there's another way. Let's say that the universe is a bubble, not just a sheet of paper, but a bubble. And the bubble's expanding. That, of course, gives us the Big Bang Theory. We're like ants living on the surface of the bubble. And then the question is, where did the bubble come from? And then you realize, my God, the bubble came from a point outside the universe because the universe is the skin of the bubble. You realize that the bubble is expanding in something bigger than 2 dimensions. It's expanding in the 3rd dimension. So in other words, what lies outside the bubble? Hyperspace. We are living on a bubble, floating in a bubble bath of other universes. And the bubble bath of universes is the multiverse, and we're just nothing but one bubble in hyperspace. Okay, well, moving on, let's take another question. Of all the books that you've written, what is your personal favorite? Well, I have 2 personal favorite books. One of them is professional. I wrote a book called Introduction to String Theory, which gives you an introduction to the 10th dimension, 11th dimension, M theory, and all that, wall-to-wall equations. Okay, so this is not for the weak of heart. This is for 3rd-year grad students that are initiating a serious program in theoretical physics. That's one of my favorites. My favorite popular book is Hyperspace, because even as a kid, I used to watch the carp swimming in a shallow pond in the Japanese tea garden in San Francisco. And as a child, I asked myself a question. If I was a fish, what would the universe look like? And I realized that the universe would be 2-dimensional. My eyes could only see the left and right directions of a pond. The universe was 2-dimensional. And if there was a scientist in that 2-dimensional pond, and we talked about the 3rd dimension, the scientist fish would say, bah, humbug. There's no such thing as the 3rd dimension. The pond is the universe. The pond is everything. And then as a child, I dreamed about reaching down and grabbing the scientist fish, lifting the scientist fish in the 3rd dimension into hyperspace. And then the question is, what would the carp scientist see? He would see beings breathing without water, a new law of biology. Beings moving without fins, a new law of physics. And then I dreamed of putting the scientist fish back in the pond. What would he tell his fellow fish? That there's a universe out there, a universe in hyperspace. And that's what I think I would tell them, tell the fish in the shallow pond. Okay, here's another question that has come in. How did you make the change into popular science, and how did you wind up doing your own shows? Well, first of all, I'm a research physicist. My world is a world of equations. I spend all my time manipulating equations in the 11th dimension. That's what I do for a living. But you know, physicists have hobbies. Einstein used to play the violin. He was an accomplished musician. In fact, a lot of mathematicians like to play with musical instruments. String theorists, for some bizarre reason I can't understand, like mountain climbing. That's right. Quantum physicists like mountain climbing. And in fact, one of my acquaintances who actually was instrumental in showing that string theory gives us a 26-dimensional universe, he died very tragically. He died in a hiking accident. But I don't like to hike so much, and I don't play the violin. What I like to do is lecture, talk to people. You see, when I was a kid, when I was 8 years old, I went to the libraries and I tried to find everything about the fourth dimension, everything about relativity, about space warps, and I found nothing, absolutely nothing in the library to answer all my questions. And then I said to myself, when I grow up and I become a theoretical physicist, I want to make a promise to myself. I'm going to write books, in addition to doing research, write books about the fourth dimension, about other universes, about hyperspace, about all the things that fascinated me when I was a kid. Okay, let's take another question because we have so many coming in. Here's a question. Looking back at the books you've written, like Visions and Physics of the Impossible and Physics of the Future, is there any scientific technological development today that has surprised you? Well, the answer is yes. I talk about many revolutions: the artificial intelligence revolution, robotics revolution, biotechnology, space travel. But then I realize, of course, that when you make predictions, you have to be careful because these predictions cross-pollinate each other in ways that are very impossible to predict. You can more or less predict the sequence of artificial intelligence and the sequence of biotechnology, but who would have thought that computers and biotechnology would essentially pollinate each other to give us the burst of biotechnology today? When the Human Genome Project was first proposed, the estimate was $3 billion because it would cost $1 to sequence one base pair. Since there were 3 billion base pairs that had to be sequenced, it cost $3 billion. Now you can pretty much sequence your genome for a few $100. What happened? Automation, computer technology, artificial intelligence. We now realize that genetics is a math problem. And that has given us a tremendous head start using cheap computers, cheap automation to analyze the digitized information coming out of the Human Genome Project. So it was the cross-pollination between computers and biotechnology that surprised me to the point where a $3 billion mission to sequence our genes can now be done with just a few $100s. Here's another question. Of the plausible, impossible ideas you mentioned, which do you believe is the most likely to come to fruition? Well, I think if you were to have a crystal ball and look 10, 20 years into the future, of course, space travel is already on the agenda. We're going to go back to the moon in 2024, gone to Mars perhaps after 2030. But I think that one of the technologies that are going to come to be is the Connectome project and perhaps the foundation for BrainNet. The human brain is a black box. Just a few decades ago, we knew almost nothing about the wiring, nothing about the mechanics of the brain. Now with MRI scans, we can see the living brain, messages in the living brain ricocheting like a ping pong ball, ideas being formed in the living brain. Now we can extract images, memories from the living brain. Who would have thought? Now, of course, we're still down the line where we can now extract emotions, feelings, sensations. We're not there yet, but I think that that's coming. And maybe further down the line, the internet will be the future of the BrainNet. Here's another question. What happened before the Big Bang? Well, Stephen Hawking used to say that if you want to see a physicist blush, ask him about what happened before the Big Bang. He also said that scientists are the only scientists who do not blush when you mention the word God. Well, let's talk about that. You see, string theory is a theory of the multiverse. Therefore, it gives us a theory before the Big Bang. But of course, we want hard evidence. How do you get hard evidence before the creation of everything? Well, as I mentioned, LISA is on the books. It's been canceled, delayed a few times. But LISA is a gravity wave detector that'll detect not just radiation from 300,000 years after the Big Bang, but radiation from the instant of the Big Bang. That is incredible. Within a trillionth of a second, we'll have information about the instant of creation. Now, the hope is that we can run the videotape backwards. Run the videotape backwards just a fraction of a second and get an idea of the radiation that existed before the Big Bang. See, string theory takes us before the Big Bang, but we don't know which universe is our universe. In a multiverse of universe, the theory has, in some sense, no predictive power. It's a theory of anything, not a theory of everything. In other words, it's a theory of all possible universes. But we want to know about our universe, not just a theory of all possible universes. But once we have radiation from before the Big Bang, then we can compare it to the predictions of various pre-Big Bang theories that are now being circulated to see which one is correct. Now, personally, I have my own point of view. My own point of view is that ultimately, it's a math problem. You see, I personally think that string theory will eventually give us simple numbers like the mass of the proton, the mass of the quarks, the interactions of the nuclear force. In other words, the world of today. If we can get exactly the world of today, that is the mass of the electron, the mass of the proton, from string theory, game over. That would be the clincher. That string theory would give us absolute experimental evidence of the world of today, not just the world of the Planck length. But if string theory has that predictive power, then I think game is over. Okay, well, let's go on because there's so many different questions here. Here's a question about my book, Visions. In Visions of the Future, you quoted 3 revolutions to come: intelligence, biotech, and quantum. Today, 13 years later, how long have we come along these 3? Well, I think of the 3, the biotech revolution has raced ahead because using the Genome Project, using artificial intelligence, using automation, we're now sequencing all of life itself. So I think that pace has quickened faster than I predicted 13 years ago. And the reason is because of the cross-pollination of these technologies. Now, intelligence, in terms of Moore's law, I even stated in the book that Moore's law will eventually slow down. And that prediction is happening right now. Moore's law, that computer power doubles every 18 months, is slowing down. And do we have a replacement for silicon power? The short answer is no. We have glimmers of hope from quantum computers, but perhaps the most immediate successor to silicon would be a molecular computer, molecular transistors, perhaps made out of graphene or other kinds of nanotechnological substances. So as I predicted, we are gradually approaching a dead end. We have to find a replacement for silicon, and it may come from nanotechnology, graphene, things like that. We don't know for sure. Okay, and then let's move on. Which of these possibilities is most likely to happen in the next 30 years? Well, I think one prediction that is going to have a tremendous amount of verification is, of course, the space program. As I mentioned, we're going back to the moon. Humans will walk on the moon just in the next few years. And in fact, Elon Musk is selling tickets commercial tickets to the moon. And in fact, there's a Japanese billionaire that even bought up the tickets. That's right. You can actually buy tickets to go to the moon. So I think that that's one way in which the predictions of the next years are going to be satisfied, because one, rockets are reusable now, prices are dropping. It costs $10,000 to put a pound of anything into orbit around the planet Earth. That number is going to drop. That number, by the way, is comparable to your weight in gold. Think of your body made out of solid gold. That's what it costs, roughly speaking, to put you just in orbit around the planet Earth. Okay, let's take another question. There's so many. If we hypothetically manage to survive a journey through a wormhole, how do we know if we wind up in another universe or not? Well, of course, we're not there yet. One possibility is, and several physicists have discussed this, that wormholes may be a remnant of the Big Bang. That is, if the Big Bang expanded so rapidly, maybe there was a wormhole there, a quantum fluctuation back then that would also expand with the expanding universe. And then we can play with it. Then we can send objects through it to know what's on the other side. Now you may say to yourself, isn't there an event horizon? Isn't it a one-way trip? And the answer is no. Wormholes are in principle transversable. They don't have a finite event horizon like a black hole, which is a point of no return. You can actually go back and forth. And so that's another possibility of being able to know where you're going. Otherwise, it's a crapshoot. You don't know where you are going if you go through a wormhole. Now, the Alcubierre drive, you do know where you're going because you're compressing the space in front of you, expanding the space behind you, and then instead of going to the stars come to you, so you can aim yourself. The problem is, I talked to Alcubierre about this, the problem is twofold. One is, of course, the energy. You need positive and negative energy to create the warp bubble to begin with. And second of all, communication. The warp bubble cuts off communication between the inside and the outside of the bubble. So you have to know how to steer it. You have to know how to give orders to the warp bubble as you go faster than the speed of light. And what is it like to be inside the warp bubble? You feel nothing, absolutely nothing. The warp bubble has basically disconnected itself from your familiar universe, and you feel nothing as you go faster than the speed of light. Okay, well, here's another question. Although we can, to some extent, record memories and monitor minds, can we decipher them without pouring them back into a brain? Well, like I said, right now we're at the very beginnings of this technology. It was only about 3 years ago or so that the first memories were recorded in the hippocampus of a mouse. That memory can be then put into another mouse. And in fact, at MIT, they've even been able to use distorted memories, false memories. So false memories can now be manipulated, and that's dangerous because what happens if you fake a memory of somebody shooting somebody, put it into the brain of an innocent bystander, and the bystander has a memory of him killing somebody. So do you think, therefore, that this could cause problems for the legal justice system? Because how do we verify eyewitness accounts when memories themselves can be tampered with? Okay. Okay, well, here's another question. Thank you for this mind-bending talk. If we go back to everything not forbidden is compulsory, how can we be certain that we're not, in fact, living in the matrix? What are the main laws of physics that were violated to make this impossible? Well, as I said before, we physicists believe that everything that is not forbidden is compulsory, usually a symmetry. A symmetry or conservation principle is a principle that makes things impossible. And therefore, we think, therefore, it is impossible because of a principle. But you see, with time travel, we've looked for that principle that makes time travel impossible. It's called the chronology protection hypothesis, and failed. That doesn't mean that time travel is possible. It just means that we've not been able to disprove existence of time travel. Now, in the Matrix, well, you see, the problem with the Matrix is that our universe is not deterministic. If our universe were deterministic, then our universe could in fact be a motion picture. Somebody pushed the play button and has been watching this drama unfold on his or her computer screen. That's a possibility. But our universe is not deterministic. It is quantum mechanical. Now, with our most advanced computers, we can't even predict the weather. Forget the Matrix. We can't even predict the weather. In fact, the smallest object that can simulate the weather is the weather itself. That's right, the smallest object which can simulate the weather is the weather. That's how complicated Newtonian mechanics is when you start to talk about trillions and trillions of particles. Reality is even more complicated. In reality, we have the quantum theory, which gives us an infinite number of universes. So in other words, the universe is most likely not a computer simulation. Okay, here's a question that, of course, a lot of physicists are working on today. What's the problem with proving or disproving string theory? Well, testability is done indirectly. How do we know that the sun is made out of hydrogen? Well, we've never been to the sun. We can't touch the sun. So how do we know it's made out of hydrogen? By looking at sunlight, indirect signals from the sun with a spectroscope. Same thing with string theory. Dark matter. If we find dark matter, and dark matter may be found anytime now with our detectors, many of which are looking for dark matter in underground vats of liquid under the surface of the Earth. If we find dark matter, then we can look at what are called coupling constants between different particles. If they agree with the photino, a supersymmetric particle predicted by string theory, then that would go a long ways to proving that the theory is correct. Another way is to look for deviations from the inverse square law. Every high school kid learns that Newton's theory says the farther you go away, the weaker gravity is by the inverse square law. But we've never measured that at a short distance. We should be able to measure the inverse square law at a very short distance, like your living room, and therefore show that the inverse square law is sensitive to the dimensionality of space-time. If the universe were four-dimensionally in space, it would be the inverse cube law, the inverse quintic law, the inverse sextet law, rather than the inverse square law. And so that's another way to prove or disprove the correctness or incorrectness of string theory, is to look for higher dimensions. And then parallel universes, using things like gravity wave detectors that examine the instant of creation with the gravity wave detector. That may give us clues to the pre-Big Bang universe. And then we would have numbers by which we could then compare with string theory. That's another possibility. So again, there are many possibilities. My personal point of view is that the main problem is theoretical, not experimental at all. That any young person, enterprising young person that can calculate the mass of the electron, calculate the mass of the proton from string theory, that would nail it to the wall. Right then and there, that instant, we would say, aha, this really is a theory of everything. That is, everything in our universe, not the multiverse, but our universe, can be predicted using string theory. Okay, well, let me just take one last question. Can humans someday have the power to fight the virus and save Mother Nature from a pandemic? Well, my answer is yes. I think that artificial intelligence will give us the cure for the next pandemic. We will have artificial intelligence sensors distributed throughout our world, analyzing viruses instantly as they are created in real time to give us an early warning system. So I think artificial intelligence, able to digest this massive data from trillions of sensors in our environment, will ultimately give us the cure that is the way in which to defeat the coronavirus. Okay, here's a question. To send your mind thoughts to a distant place in the universe, surely you would need a receiver already in place to receive the laser beam in the case of laser porting that you mentioned. And your answer, your question is absolutely right. There is a problem with what I just mentioned. In order to laser port your mind and consciousness to the moon, there has to be a mainframe computer on the moon to download your consciousness and insert it into an avatar. So in other words, somebody has to go to the moon the old-fashioned way. First, to set up a receiver to receive the laser beam, and then to create an avatar, and then to energize the avatar with your consciousness. So the answer is yes. The first generation that sets up this device would have to be at sublight velocities. It's sort of like the transatlantic railroad. The people who laid down the railroad at a very slow pace. It took years to lay down the railroad, decades of work. But once it was laid, then of course it transformed North America, transformed the world with the railroad system. Okay, here's another question. Philosophy. What are the philosophical implications of BrainNet that I mentioned? Would we lose the cultural diversity and intricacies of society and give a majority population the purpose to strive for the better? Well, some people think that the internet, not just BrainNet, but the internet would destroy local cultures. I don't think so. Take a look at the elites of the world today. The elites of the world are bilingual. They speak one European language, like English, but they also speak the local language, and they're fluent in their local culture. They are bicultural. In the future, when we have what I call the type 1 civilization, that is a planetary civilization, people will be fluent in two cultures. One, the planetary culture. There will be a type 1 planetary culture emerging. For example, people will probably speak English or a variety of European languages. Already we see the Olympics. Already we see Chanel, Gucci, a planetary fashion. We see the beginning of a planetary culture, but they will also be fluent in the local culture as well. So even in a type 1 planetary civilization, people will still be bicultural. We'll still preserve the culture of our ancestors. Okay, well, I think I've run out of time. So it's been a real pleasure answering your questions. And again, go to my website, mkaku.org, mkaku.org, and there's a lot more on my website. It's been a real pleasure.
Professor Kaku, as the Master of St. Cross, which is the home of the Centre for the History and Philosophy of Physics, could I just thank you for a tremendously, as someone said in the questions, mind-bending talk. You started by saying that we needed to understand the future through a firm foundation in physics. As a non-physicist, I was then slightly alarmed when you said that string theory wasn't for the weak of heart. But I was extremely grateful that you then chose to write and talk for those of us who are not string physicists or theorists, to help us who aren't even carp scientists, but just plain old carp swimming around in the pond, to understand that what we may have thought of as science fiction could just perhaps be science that we haven't quite understood yet and will be coming at us down the track. You've answered so many questions, which is incredibly generous of you. And I can tell from all of the comments in the chat that people have really appreciated this evening's talk. Thank you. Our minds are well and truly bent and expanded, and we're all going to go and learn more from you in the future. Thank you so much for your time tonight.
Thank you. My pleasure.